Good. Okay. Thank you. I think we can start. So today I will present a paper called Optimally Deceiving a Learning Leader in Stackelberg Game. So this is a paper that was presented in NeurIPS 2020 and NeurIPS, yes, NeurIPS 2020, and I will give a very simplified version of it. So because the paper is 18 pages and we have less than 1 hour. But I think the core of the paper can be shown very easily. Please interrupt me if there are questions. So I will try to use this utility here to show the basic results. So first of all, what is the setting? So the setting is the setting of a Stackelberg game. Stackelberg game is a game in which there are two types of players, a leader and a follower. So the leader is the one who takes the first move, takes the first decision, and the follower takes another decision in response to it. So, but today I decided to simplify a bit this, to make it a bit more concrete. So instead of a leader, I will talk about regulator. So the regulator is like the government or some authority in general, and the follower is a user. So the regulator has the goal to maximize social benefit, or also called social welfare. For instance, you can imagine the regulator wants to maximize energy savings or maximize CO2 reduction, for instance. While the user, so the regulator thinks about the good of society, while the user thinks about the good of themselves. So the user wants to maximize a utility that is a selfish utility. And so the user has to choose among different alternatives. So let's see what are the decisions of the regulator and of the user. In the setting I'm explaining, the user has different alternatives that I denote with A. Let's take a practical example. For instance, the user can be a traveler, and every day they have to decide whether to take the train, the car, etc., etc. So these alternatives are, in this case, to do the trip by car or by carpooling or by public transport or by what else? Walk, bike, or maybe even no travel. Of course, each alternative has a certain social benefit or social cost, the contrary of social benefit. Because if the user chooses alternative car, they pollute more than if they choose alternative walk, for instance. Okay, so this is alternatives of the user. And then on the other side, we have the government, the regulator, who can apply a certain policy, which I denote with Y. With this policy, the regulator wants to influence the choices, the alternatives of the users. For instance, the regulator could, an example of policy is an incentive proposed to a user. For instance, the government could say that, okay, if you go by car, I will give you €0 as an incentive. If you go via carpooling, I give you €1. And actually, currently, in Ile-de-France, if you go via carpooling, the government puts €2.50 every time, €2.30 every time to fund your trip. So it's not absurd what I'm saying. If you go by public transport, maybe the government will give a subsidy of €2. If he goes by walk, €3. If he goes by bike, €3. No travel, €4. I mean, it's just an example. Maybe it's a bit absurd. So So with these incentives, the regulator tries to steer the choices of users towards some environmental friendly choices. So let's see now how the alternatives are decided. And so how the choice among alternatives is decided by the user and how the regulator decides the policy. So let's assume that the regulator applies policy Y and the user chooses alternative A. So in this case, the user will have a certain utility. So utility can be whatever you want, but just to give some practical idea, this utility can be some constant. When I talk about utility, let's assume it's euros, okay? So it can be some constant that indicates how much the user prefers that mode naturally. You know, maybe I prefer car, and so for me, my inherent utility is 5 euros if I go by car. Instead, if I go by public transport, I hate it so much that my inherent utility is less, 3 euros, for instance. So this is a constant. Then, of course, the utility depends on the time I take by that mode. So beta times the time I go with that mode. And this is a negative utility because the more the time, the less my utility. We can also put the ticket, you know, if there is a ticket to pay, I mean, the more the cost of the ticket, the less the utility. And then plus yi. So I said that y is a policy and it's a vector. So we have y, the vector is composed by y carpooling, y pt, etc., etc. So if the user chooses a certain alternative I, they will get a subsidy, an incentive yi. And this will influence the utility of users. Okay. So this thing that may be a bit crazy, maybe, but this is how economists work. You know, there is a framework called discrete choice modeling, which was proposed by McFadden, who is an economist who won the Nobel Prize for this thing, in which when they tried to model how people choose among different alternatives. And they assume that each user has a utility. And then the difficult part is how to estimate this utility, okay? Because it's something immaterial. But still, they developed a big theory that is used in marketing, in policy decisions, etc., etc. So please tolerate the high level of abstraction of this thing. So in this utility, we can distinguish two parts: an inherent utility that indicates the preference of the users toward a certain alternative, and that doesn't depend on the incentive, and then the incentive. So the utility is split in two parts. So this is what happens to. So, and of course, you can imagine that the user chooses, when the regulator applies policy Y, the user chooses the alternative that maximizes their utility, right? Then let's see how the. I have a problem with my keyboard. Okay. So let's see how the what does the regulator do? So the regulator has what I said, a social benefit to maximize. So when the regulator applies policy Y and the user chooses alternative A, there is a social benefit that is created. And for instance, you can assume that the social benefit is some gamma. So this is beta, but I should call this differently, like this, okay. So some gamma, the CO2 savings that we achieve by convincing the users to take alternative A to work, for instance, instead of private cars, minus yi. Because if the government gives you some incentives, it is taking these incentives out of his pocket. So it's a negative social benefit. This is how economists reason. Okay, but again, this is just an example that will make my narrative a bit more direct. But the paper is in general about Stackelberg games.
Question.
Yes.
Is the utility of a user dependent or independent of the actions of other users?
So in this setting, it's independent because they have one leader and one follower. But in general, it's not.
The point is, regarding the policy, the utility of the user and the regulator are both linear in the policy?
Not necessarily.
Here they're
Yeah.
using the same value.
Yes,
But
yes.
there could be different utility functions of that.
Absolutely.
policy. Okay.
Yes, yes, yes. Yes. Thank you for the question.
I have also some question maybe in the chat there.
Okay, maybe I can see it here. Chat. We can't hear the question. Okay, yes, you're right. So the questions were two. The first one is the utility of a user depending also on other users, like if there is congestion, etc.? And the answer is not in this paper. So they have just one leader, one regulator, and one user. That's all. But in general, in reality, this is not true. And the second question was, is the utility a linear function of the policy? And the answer is not. It can be whatever. And there is another question.
Yeah, and you have only one user? Or
Yes.
Okay.
Only one user. So it's like each user is independent of the other. So the regulator interacts with each user independently. So it tries to get the most benefit from each user independently.
So he doesn't have to choose his policy based on the different utilities of different users.
No, in
Okay.
this setting, no. Then in reality, yes. Yes.
And last question, do you assume that the objective and the utilities are linear functions, or it could be anything?
Yeah, it can be anything.
Okay.
The utility function can be anything. Then it's true that economists like to use linear functions, but they can be anything.
I think this score of the government should be the average or the sum of some cost of all the people.
Yeah,
only...
that is true.
Yeah.
But if we assume that every user is independent of the other, that is the assumption we make, then maximizing the sum of the benefits you can get from each user is equal to maximizing what you can get from each user independently. So this is the simple assumption they make. Yeah, so this is the thing. So if there are no more questions, I will continue. So yeah, so let's say that the best response of the user to a policy Y is an alternative that is in the arg max of UYA, right? The user chooses the alternative that maximizes their own utility. And the optimal policy is the one that maximizes social benefit, which means it's in the arg max of all the possible set of policies, assuming that when the government applies Y, the user chooses best response Y. Okay. So both they try to maximize their own goals, and there is an equilibrium when both conditions are matched, meaning that YA is an equilibrium if the regulator cannot gain more benefit if they change a bit the policy, if they change the policy. And also, in the same moment, the user cannot improve their utility by choosing something else than A. So this is the definition of an equilibrium in Stackelberg games. So then you can see that what is the utility that the user collects? Well, the utility is Y, U. Since the regulator will apply the best policy, we know that this is the policy that will be applied, that I defined here. It's the best policy possible. And what is the action of the user? Well, it's the best possible here. So B, P, Y star. Okay. So this is the utility that the user will collect. And the social benefit for the society or whatever it is, it's this one. Okay. This is the situation where everyone is honest, etc., etc. Now, a question is, can the user earn more, collect more utility than this one? Does anyone have any idea? If you're a user and you are subject to these incentives, etc., can you increase your utility even more, the equilibrium?
By lying?
By lying, yeah, exactly, by lying. So a famous example is in Brazil, the government was giving incentives to underemployed people, and there were people who were on purpose underemploying themselves, or they were declaring they were underemployed to get an incentive. So this is what this paper is about. In fact, the paper is called Optimally Deceiving Learning Leader in Stackelberg Game. So the paper is about a manipulative. Yeah, manipulative user. I mean, that is a user that manipulates the regulator in his favor, or also called deceptive user. Okay.
Andrea?
So, yes.
Andrea, sorry, question.
Yeah.
In this paper, you said that you consider a single user, but will the framework that you will present extend to several users?
I think it's not very easy. And I didn't see a lot of papers on that. So I'm not familiar with this domain. I'm slowly entering into this domain because I'm working with a stagiaire, Alessa, who is here. And I hope to start more research and a PhD on that. But from what I saw, there is no case study of a deceptive behavior of users, taking into account congestion, etc., etc. The only papers I saw are always one leader and one follower that may deceive.
I was thinking not necessarily a user having, say, connected utility, but simply, for example, this one prefer using the bike, this one prefer to walk, this one prefer to use the car. And so they are independent, but they have their own utility.
Yeah. If that, in your case, this paper extends to that situation as well, because you can then isolate the interaction between the regulator and each of these users and analyze the game between the regulator and user number one, then analyze the game between regulator and user number two, etc., etc., etc. Since they are independent,
you would have a per user policy in this case. You could you wouldn't envision a global policy as would do, for example, the government to incentivize people to use the bike or something like this.
Exactly. So this is what is called a personalized policy. That is why I discovered this topic, because I was working on personalized policies.
Okay.
And in personalized policy, exactly what you say happens.
Okay.
Thank you. The same question was from Ludovic. Okay, so now the question is, what can a manipulative user do? Can he really mislead the regulator, or there are some limitations? So the basic result of the paper is that under mild assumptions that you will see, a user can induce any equilibrium xj different than the true equilibrium, that is y star, best response y star. So maybe a better way to frame this is, I mean, the user can drive the regulator, can convince the regulator to apply the policy the user prefers under some assumptions. Okay, so this is a very negative result. But basically, we can fool the government as much as we want, almost, and all the social benefit that these kind of incentive policies promise will go away. It's happening now. Government is giving a lot of money if you carpool with other people. So at the end, what people do is they don't take public transport. They prefer to carpool because they get some money. So at the end, the policy was meant to reduce CO2, but maybe it is increasing CO2 because people are fooling the government. But yeah, and we can think about other more general cases. Yes, so let's see how to formalize this thing. So maybe the first thing I can tell is a lemma. Yeah. So when you said the user can lie, it means that the user can adopt and declare a utility function, a fake utility function. Let me write it. Fake utility function that is potentially different from the true utility function. Okay, so that the regulator will apply the best policy X under the assumption that the user has this fake utility function. And so the user can then collect the true utility function that comes out from this policy. So what it is important to understand, where of course J is the best response to X. So what you have to understand is that the user can adopt a fake utility function just to fool the regulator, but then the utility they collect is based on their true utility function. Okay. So if that is clear, let's see how to construct this behavior of the users. So, and I will define two things before. So the first thing is socially worst alternative. So all these things are not written in the paper. I think it's easier to talk in these terms to show the same results of the paper in a shorter way. So for whatever policy that the regulator can apply, I will call WY the socially worst alternative, the one such that it minimizes the social benefit phase to Y. So this alternative is the worst one. I mean, a user that adopts this alternative is I would call it adversarial user. Is a user such that when a government proposes a policy, he behaves so as to destroy the society as much as possible. So this is not what the user will actually do, but he can threaten the regulator. He can say, look, if you don't apply the policy I want, I will destroy society, basically. I will, every time you do a policy that I don't like, I will choose the best alternative for society. So it's a way to force the regulator to do what you want. I mean, it's a bit Trump-style negotiation. And then I would also define the what I call max worst social benefit. Social benefit. I define this as M, that is the maximum that the regulator can hope to get when the user is adversarial. Okay, so assume that you know your users are adversarial. You have to choose the best policy that maximizes social benefit, despite the fact that your users are very nasty. So with these two definitions, I can then, I can then show a very simple lemma. And I don't know how much time I have. Okay. So very simple lemma is, so suppose that the user wants to induce a certain policy, a certain equilibrium xj. So the user wants to behave so that he forces the regulator to apply policy x, and then he chooses j. And also assume that this equilibrium that he wants to induce is as these characteristics here. What does it mean? So let me complete and then see. So then there exists a strategy of the user to induce this thing. And now we will see what is this strategy. So basically, the user can impose any equilibrium he wants, provided that this equilibrium is not so bad. So the social benefit of this equilibrium can be like very poor, but not so poor. It should be at least equal to the larger than the max worst social benefit. So this means that the user cannot really impose something that is very, very bad. The badness of the equilibrium that the user can impose is lower bounded by this M. So it's easier to prove when it's bigger, I think. And I don't remember it. So the question was, this inequality can also be equality. I think in the paper, they also use the equality, but here we use the inequality. It's easier. Okay, so I don't know if it is still clear what I'm saying. Okay. So does any one of you have a suggestion of what this behavior can be? How can you force the regulator to apply a policy X that you prefer? And you can use the threatening strategy, right?
You say that you would take the worst choice, I guess, if
Yes.
it doesn't opt for what you want.
Exact. So this is the thing. So the thing is, the policy is this one. So if the regulator applies a policy that is different than what the user wants, then the user will choose the socially worst alternative. Okay? Otherwise, if the regulator does what the user wants, the user will choose the J, because this is the equilibrium they want to impose. Okay, so now to prove this thing is quite simple. So we have to prove that if the user behaves like that, the government has no interest in giving something that is different from X. This is what we want to prove. So
just a remark, Andrea, if
yes.
I may.
Yeah, please, because
I guess
it makes everything
I guess
clearer.
this is a family of policy because, for example, assume that I want to earn a lot of money by taking my bike. I don't care about the incentives that are given for, I don't know, the public transportation or whatever, while I have what I want in terms of bike. So I guess that what you call uh, Y or X, rather X belongs to a family of Y, if I'm correct, no?
Yeah. So all the possible policies are a set P. This is so Y and X should be in this set P. So the
Okay.
regulator cannot leave this set undecided because maybe otherwise he would risk to pay $1,000 million when a guy decides to take the bike, right? So the policy should be the set of possible policies should be well defined.
Okay, so Y is a set of policies actually in this case.
Exact. The big P is the set of policies. So Y and X should be anyways in P.
Mm. Okay.
And it should be a bit limited.
Okay.
I just thinking also maybe the regulator can also impose his choice to the user.
Yeah.
But this is if the incentive can be negative. Do you suppose that the incentives are always positive in your case?
So now I'm talking always in terms of positive incentives, but I think everything would still hold if we have negative incentives, which means it's pricing. I think it's the same, but yeah, maybe, I don't know. And actually, yeah, the regulator can impose something different. But let's see what happens to the regulator if he imposes something different. So let's assume that the regulator imposes a certain Y that is different than X. Okay. Then, if he does so, and the user adopts this behavior that we are saying here, well, the user will be adversarial. So user chooses this thing, the socially worst alternative. So at the end, the social benefit will be this Y, which is, of course, less than or equal to the maximum over all the Y of this thing. Okay. And which by definition of M is equal to M, which by hypothesis is less than Bxj. So at the end, it's not convenient for the regulator to impose anything else than X because he will obtain a social benefit that is worse than what he could obtain by just obeying to the user, right? Okay, so I showed you that if the user threatens the regulator should accept, should behave according to the user, provided that, again, this is important, that the equilibrium the user wants to impose is not extremely bad. Okay. But now imagine the user acts directly like this, like he says clearly, regulator, I'm going to threaten you. If you don't do what I do, what I want, I will destroy society, etc. Of course, the regulator can easily spot a user who behaves like that, and he can take actions. For instance, he can say, okay, for this kind of arrogant users, I will not give an incentive, or I will put you in jail. It depends on the states in which you are. So what is interesting for the user is to, at the end, behave in the same way, but in hiding this kind of threatening behavior, so that the regulator cannot distinguish this user from a honest user. So do you have any idea how the user can basically apply this kind of strategy, but without saying it out loud? Any idea? 10 minutes. Well, the idea is simple, and it is similar to what I said at the beginning. So the user has to find a fake utility function and behave according to the fake utility function, so that, and it has to construct this utility function so that at the end, this behavior emerges. But if it does so, the regulator cannot say, oh, you are threatening me. No, the user can say, no, I'm just maximizing my utility, and my utility happens to be this one. So I'm honest, I have the right to behave like that. And I'm sorry for you, regulator, you have to apply the X I want. Okay, so now the next slide will be how I can construct this kind of utility. And so should I change slide? Yes, I change slide. Well, no, maybe I will do this. So if this is clear, I will remove. And now let's construct this thing. So this fake utility is, okay, it's for any y and any a is equal to minus b y a. Okay. If a is different than j, and I think that is a bit more complicated, but it is still very simple. Yeah. Alors, minus b y k, I will define k in a second, plus b x j minus b y j if a is equal to j. Okay, this is for any y and I, the utility function is this. And k is defined as it's in the argmin of all the alternatives except j that minimize this thing. Okay, so it seems a bit strange, but you will see that it works perfectly. So now what I want to show is that if the regulator declares this utility function, he will basically be authorized to act adversarially, and the regulator cannot say anything. So, okay, 7 minutes. So let's see what happens directly if the user adopts this utility function and the regulator applies any policy y different than x. So now what I do? So I do this, I want to make it smaller. Sorry, I do this because I want to have all the things here. Okay, So please tell me if it's too small. If it's too small, or is it still okay? It's okay. Okay. Now, suppose that regulator applies, I start from here. If y is different than x, what happens? Yeah, so if y is different than x, of course, the user will choose the alternative that maximizes his utility. So he will choose a prime, let's say, such that u y a prime is larger than any other thing. So it's larger than u y a for all a. Okay, and fake. Okay, and now we want to show that this is worst. This brings a utility that is worse than what you would obtain with xj. So let's assume that this best action is not j. So if this is the case, we can rewrite, u tilde here as this line here, right? This is the definition. So I will write minus b y a larger than a prime, sorry, larger than this one that I write in this way. So larger than minus b y y a for all a in a minus j. And then I will show also that, so actually this thing means two parts, that mu tilde y a prime should be larger than mu tilde y a for all the a in big A except j, but also that, I go fast, but u y a prime should be bigger than u tilde y j. Okay, because this thing is bigger than the utility you collect with all the actions. So I can divide the actions that are not j and the action that is j. So let's first work with the actions that are without j. So this means that b y I prime is less than or equal to b y a for a and j. Okay. And by definition, this is less than or equal to m here, which is by hypothesis less than bxj. Okay, so okay, so I should also do the same reasoning for what happens when the action is j, but I will not do it. There are only 2 minutes. But this is a proof that if if the user adopts this fake utility function and the regulator applies y that is not what the user wants, it's worse for the regulator. This is basically all the what the paper says. Then why is the paper 18 pages instead of just some slides? It's because there could be multiple equilibria. Okay, so in this so when there are multiple equilibria, nobody knows which equilibrium will be actually chosen. So this means that the regulator, it's not so easy for the user to fool the regulator, because at the end, the user can force xj, but maybe there is another equivalent equilibrium where the game will go, and the user will not have the result that he wants. Okay? So what I showed is just that xj, that is the equilibrium desired by the user, is actually an equilibrium, but it might not be the only one. What they show in the paper is that it is actually the only one, but it takes 18 pages. So I chose not to do it. So I think, yeah, it's 12, so I don't want to take more time. If there are questions, it would be good. Thank you. No. Basically, I told what I said, then I should continue other calculus, but since I did it fast, je vais mélanger mes pinceaux. It's better not. But I hope that the spirit is the important thing. Actually, all these papers are based on understanding how one can build a fake utility function. And it's interesting to observe that this fake utility function is mirroring the opposite of the social benefit. So you simulate as a user the fact that you have more pain, the more society is good. Okay, so and of course, if you act like that, the regulator, you can fool the regulator actually to in a way that is favorable to you. This is the spirit of the thing. And so you may think that what I told you is quite simple, but still the literature about this kind of things, deceptive behavior in Stackelberg games, etc., is quite recent. This paper is 2020, and then there are papers 2022, 2024. One thing I want to emphasize is that they say optimally deceiving a learning leader in Stackelberg game. Learning. So they added learning in the title because they submitted to NeurIPS, which is a machine learning conference. But there is actually no learning at all in the paper. And in this kind of papers, there is no learning at all because they assume that the user can declare the fake utility function and the regulator immediately believes him. And this is my interpretation. There is no learning at all. And indeed, since reviews in NeurIPS are on open review, so everybody can read the reviews, I saw that some reviewers were saying, okay, the work is interesting, but it's not machine learning. And they replied, they or another similar paper, they replied, no, but it's machine learning because there was a previous paper on the same topic with the same methods that was published in NeurIPS. So this is, and so this is why they got a NeurIPS paper. What I would like now to do is to actually introduce the real learning, meaning that now the regulator, if you want to fool the regulator, you have to act consistently according to your fake utility function. This means you cannot optimize your true utility function. So fooling the regulator does not come for free. You have to behave against your own goals for a while to convince the regulator of your fake utility function. This means that you have to pay a cost. And so sometimes it may not be so convenient for the user to fool the regulator, at least not so easily and not as much the user wants as in this case. That is nothing. Any questions? No? Okay. Good. Thank you. Thank you.